Now let's look how the situation changes when we look at a second order integrated rate law expression. So here we have A becoming B plus C. And if we would write out this rate law, we know that the rate is going to be equal to K times the concentration of A to the X power. Well, if we know this is a second order reaction, that means this A has to be squared, okay? Because the overall order is going to be the sum of these exponents. All right. We can also write the rate as the change in concentration of A per change in time. That's going to equal K times the concentration of A, that quantity squared. So if we rearrange just like we did in the first order case, we're going to get negative dA over A is going to equal K times dt. If we again go through and make this positive and this negative, and then integrate from A sub 0 to A at any time t for both sides, we're going to get the following. Okay, since this term down here in the denominator is squared, our integral is going to change to 1 over A at any time t minus 1 over our initial concentration, and this is going to equal KT. So if we rearrange this into y equals mx plus b form, we have 1 over A at any time t is going to equal KT plus 1 over A naught. And now we have our second order expression in y equals mx plus b form. And when we go to plot this now, we're going to plot 1 over the concentration of A on the y-axis and time on the x-axis. When this happens, we're going to get a slope that's equal to K, and our y-intercept, or our B, is going to be 1 over A naught. So when we're performing problems and we know that we have a second order reaction, we can use the integrated rate law for a second order reaction, which is given here in this box. So this is the second order integrated rate law expression.